Yeah, so this is the first Spearpunt scientific meeting. It's going to be 1.5 hours, and it will be about the Spearpunt of quantum. Spearpunt means something like priority area. So CWI has identified 4 priority areas. And the quantum Spearpunt has basically been up and running for 5 or 6 years, ever since the inception of the QSoft Research Center. QSoft is a kind of joint venture between CWI and the University of Amsterdam, and CWI is part of this center. That's basically the CWI Quantum Spearpunt. And this meeting is sort of meant to give you an overview of what's happening at CWI on the area of quantum computing and quantum information. And it's also meant as an invitation for other groups who would like to sort of do something with quantum or collaborate with us to it's meant as an invitation for you to contact Harry or me to try to see what kind of collaborations could be set up between QSoft and other CWI groups. So without further ado, let me introduce the first speaker. That's Harry Buhrman. Harry is the founder and co-director of QSoft, co-director together with Karel-Jan Schoutens of the University of Amsterdam. And he will start with an overview of roughly 40 minutes of what's happening at CWI in terms of quantum. And if anybody has a question, please write it in the chat. And if it's important enough, I will interrupt the speaker and relay your question to the speaker. And otherwise, we can take the questions at the end of the talk. So I think that's it for me. Harry, feel free to start.
Thank you very much, Ronald, for the nice introduction and indeed the invitation to everyone to get in touch with us if they want to have more information or want to get involved into this Spearpunt. I would like to start with a thought experiment, and I always like to do that. So right after lunch, it's good to close your eyes and somehow wander off a little bit into space. And in this case, I would like to invite you to close your eyes and think a little bit about the near future, where big quantum computers exist, and you have just decided to buy your first big quantum computer online. And a few days later, you're now invited to open your eyes again. A few days later, a big black box arrives at your doorsteps, and it says quantum computer. It's a rather big thing. And now actually you're first very happy with it, but then now doubts set in and you are a little bit wondering why on earth did you buy this big machine? And it was actually quite expensive, and you bought it a little bit on the spur of the moment because it was a cool thing. It sounded pretty cool and you wanted to have it because everyone else wanted to have it. And but now it's there and now you have to do something with it and you don't know what to do with it. And so you frantically start to search Wikipedia for quantum computers, and actually there's quite a lot of entries there in quantum computing and quantum programming. And it turns out that actually it's not at all as you thought it was. First of all, these machines need to be programmed in a rather different way than you're used to. And second of all, there's a lot of problems that are not at all useful to be run on this machine. And actually the search is out for what problems are interesting and what problems it can be used for. So this a little bit futuristic thought that we just had is actually not so futuristic, as it's very close to the current time period that we live in, because small machines are already available up from 10 up to 50 qubits. You can already readily access even in paid versions on the internet online. And 50 to 1000 qubits are expected to arrive quite soon. And so this question of what are you going to do with your quantum computer is very relevant. And we expect that there is an exponential increase in the number of qubits, which we have seen so far. And we are entering here on the right-hand side, you see this little graph. We are hopefully entering the usable regime sometime soon, where these quantum computers can actually be used, hopefully, to do something useful and also faster or more efficient than classical computers can. So actually, this already happened, at least the faster part, because in October 2019, Google announced that they arrived what they call quantum supremacy, which they did via a machine that they built, a quantum computer, the Sycamore processor, which has 53 qubits. And what they did on this machine was they ran a random program. I will say a little bit more in the next slides. A random program for about 20 steps, and then that produced some output distribution on these 53 qubits. So that produced a string of 53 bits, and they repeated this many times, and that gave samples from some distribution. And the claim was that producing samples from that distribution would require 10,000 years on a classical machine. Soon thereafter, this claim was challenged by IBM, who said that we can actually produce this distribution or produce samples from this distribution by using our IBM Summit, which has 2,000 petaflops, and we have to run it for 2.5 days, and then we can actually also produce samples from that. So that's probably true, although I've not seen any data from the IBM machine. But in theory, that's true. But nevertheless, it shows that we're pretty close to entering this quantum supremacy regime where a quantum computer can do something what a classical computer cannot do. And here it can barely not do it anymore. And then a little bit more recent, in December of last year, there was a Chinese paper out in Science where they also claim to have quantum supremacy. And this time it's on a different type of machine. So it's not the same type of quantum computer that Google builds, but this one's built on light, on photons. And they claim that they have up to something like, you can see it here, 76 photons or 70 qubits. And here again, the question is there a true advantage? And of course, Google raised some issues here because there's noise in the experiment that these Chinese quantum computer experiment did. And when you factor in this noise, it's not at all clear anymore that you have quantum advantage. But again, here, this is a beautiful, fantastically big experiment. And again, this is getting very close to quantum advantage. So all of this is built on the laws and the ideas of quantum physics, and you can port them to computer science, and then you get something that is a quantum computer that has as basic building blocks qubits. And this slide is not to really go through, but somehow the main idea of these qubits is that they can be in superposition of different states. So a qubit can be in a superposition of 0 and 1. And there is a well-described mathematical formalism that describes how you have to calculate how these qubits behave if you do operations on them like a quantum program. And so all of this, what I'm going to say, may sound in the remaining part of my talk sounds maybe a bit vague, but I can assure you there is a very precise mathematical description that is the foundation of this, and that we use to calculate stuff and to compute things. So programming a quantum computer, I already said, is very different than programming a classical computer. And the main sort of idea, or the main key idea, is that you use these quantum bits to do superpositions of computations. So you can think of this, although that's not entirely correct, but you may think of this for now as doing several computations in parallel at the same time. However, there's a little snag. So if you have 300 qubits, you can do something like 2 to the 300 parallel computations at the same time, which sounds fantastically beautiful, but there is a little bit of a problem, and that is that if you want to get the answer out of that massive parallel computation, you really can't get it out so easily, because if you observe it, if you're going to look what the answer is, you will only see one of these computations, and the state has disappeared. That's what quantum mechanics describes. It has collapsed, and you will only see one computation, which is not very useful. You cannot even determine which one you see. And so now comes the nice ingredient of interference, and that's what the quantum program is. And if you can now, in a certain way, and I will show an example of this, make the paths, the computation paths that you don't want to see, cancel out by means of interference, and you can somehow intensify the paths that you want to see, amplify those, then you can make good use of this quantum computer. It's a little bit like noise canceling headphones, where you have to cancel out the unwanted noise from the outside and amplify the noise from your MP3 player or iPhone or whatever device you're using, so that you can listen to your music in the airplane. But I have some bad news here, because not every problem can be solved in this way. Actually, many problems are not prone to be run in this way. And so what we are doing in this theme predominantly is figuring out how you can tap into this extra power that a quantum computer has. This is quite challenging and quite interesting, and also quite beautiful. So what does a quantum program look like? And here it is best to explain this in terms of how a classical program looks like. And a very basic way of describing classical programs is by means of gates. And you all know that you have NOT gates, an AND gate, and an OR gate. And if you plug these together in the right order, then you can do any classical computation you wish to do. And this is a very, I would say, very rude way and very difficult way of thinking about algorithms, but nevertheless, this is a way you can think about classical algorithms, and this is the way we actually think about quantum algorithms. But we have a few different gates that I drew here on the right-hand side. We have one gate that is this control NOT gate, which is very similar to a classical gate. But the other two here, the Hadamard and the rotation gate, they are really quantum gates, and they are actually operations on single qubits. And the only 2-qubit operation that you will need is this C0 gate. And the nice story is that by plugging these gates together, you can actually implement any quantum algorithm you want. So there is this nice analog, and from now on, I will assume that we will be using these gates, and that way we will build our quantum computers. So a typical quantum algorithm, or quantum circuit, as we call it, looks something like this, where you have here your input, which is the problem that you want to solve, and you have some extra additional qubits here that are set to 0. This sort of your additional memory. And then you can see here that these gates, the Hadamard, the rotation, and these C0s are somehow put together in an ingenious way. And then at the end of the day, after so time flows from left to right, at the end of the day, you measure your qubits here at the end, and the output, the bits that you measure there, form the answer to the computation you wanted to do on your input. And in general, this will be a distribution, and but it could also be just a single bit or a single function. And so this Google experiment that claimed to have supremacy looked something like this, where you had an input of 53 qubits that were all set to 0, and then there were these layers of qubits that was 20 steps deep, and then at the end of this, you just measured the output. And think of these qubits, these gates, the C0s, the Hadamard, and the rotations, as being put in randomly. There was no other purpose than building a circuit that is hard to simulate. It didn't compute anything useful. And so this quantum paradigm and these quantum computers and qubits and quantum programs that run on them has led to a couple of nice applications that started the field in the 90s. And the first big result was that of Peter Shor, a famous algorithm called Shor's algorithm, that sort of factors big numbers into their prime factors. And this in turn can be used to break a lot of cryptography that we use today on the internet. And so the search is on for cryptography that is somehow secure or safe against this attack of Peter Shor on a quantum computer. And funnily enough, the first protocols that do that were built before Peter Shor generated or produced this algorithm, and they are due to Bennett Brassard and a little bit later by Arthur Eckert, where they use quantum mechanics itself to build protocols that are prone or that are secure against these factorization algorithms. Then something that I've worked on myself is you can also use these qubits for communication, not only for computation, but also for communication. And when you do that, you get sometimes efficient distributed protocols. And it also gives rise to something that we call the quantum internet. And you can make use of phenomena like entanglement, which are purely quantum mechanical. You don't have these phenomena in the classical regime. Then most likely the first application of useful application of quantum computers will be in the area of chemistry and material design, and perhaps also the development of new medicines, because nature itself is quantum mechanical. And for example, when we try to understand a chemical reaction, we don't know how to solve the equations that quantum mechanics give us. And we are stuck with root approximations of how nature really behaves, or how quantum mechanics predicts how nature behaves. And so it's all very logical and actually also works that you can use your quantum computer with relatively few qubits to help you understand these chemistry reactions or these material design problems in a much better way than we currently can. So this will open the door to understanding these areas a lot better, and hopefully also develop new materials and new catalysts, for example, that come out of this. And then last, we know that quantum computers, if they are a little bit further down the road, can be used to do optimization problems a little bit more efficient, or machine learning problems they can do a little bit more efficient. And here there are lots of other applications to society and industry. So let me give you one little example that I like a lot, because I think it is funny, and it shows you a little bit the flavor of how a quantum algorithm works. And that is the idea of doing a random walk. And normally random walk algorithms are on more complicated graphs than a line. But for now, bear with me, and let's focus on how a random walk works on the line. And then the idea is, of course, to port this to more complicated graphs and then use it there. So the idea is that you start in the middle of the line here at point 0, and you flip a coin, and with probability half, you move to the right, and with probability a half, you move to the left. And once you arrive there, you again flip your coin and you move to the right and to the left, probability in half. So it looks something like this. You flip your coin, you end up at position 1 with probability half, or you end up at position -1 with probability in half. And for example, when you ended up at 1, you flip your coin again, you end up at 2, or you move back to 0. And so on and so forth. And when you do this a number of steps, and I simulated here 250 steps, then you see that you get this nice Gaussian distribution where the probability that you haven't moved at all is still quite high. So you are stuck in the middle, but you have moved to the left and to the right about square root of t steps. And many of you know this phenomenon. And this is the behavior of a classical walk. But now let's do this quantum mechanical, and let's in superposition move to the left and to the right, and then do that again and again. And when I run that experiment for a number of steps and then measure, then I actually do get a probability distribution out. And I've plotted that probability distribution over time. And here it looks much nicer, or much more interesting, I would say, because here you see that if you do this quantum mechanically, you get these peaks that ballistically move to the left and to the right. And actually, the probability that you're in the middle is now much smaller, and the probability has been pushed to the outside that you went left and right. And so let me show that again on the next slide, because it took me some time to program this, and I want to show it again. So here you see the two differences. The quantum walk walks about t steps to the left and to the right, and the classical one has only moved square root of t. And now imagine that you do this walk algorithm not on a line, but on a more complicated graph. And a lot of algorithmic solutions can be cast as random walks on graphs. And now with a little bit of imagination, you can now see that a quantum algorithm could be constructed that speeds up a classical walk algorithm on a graph. And there are a bunch of examples, for example, element distinctness and satisfiability solvers and backtrack algorithms and many, many more examples that use this idea of a quantum walk and in this way speed up classical algorithms that we know. And here you see actually a nice thing, that is that a quantum walk, because it's quantum, it can also be reversed, which means that you can just undo the steps and end up back into the middle. And this is of course something you cannot do classically. If you wanted to backtrack how you went, you have to actually have a memory and remember where you are, where you were, so to speak. Okay, let me continue. And a question I often get is which problems have a quantum speed up and which ones don't? And this, of course, is something that everyone wants to know, but nobody really knows the answer because this is a very deep and difficult question. And also it really touches up on fundamental problems in computer science, like the P versus NP problem. So there is no easy answer, and there will not be one ever. But you can nevertheless roughly identify three categories of problems. The first are those problems that allow for an exponential speed up, like the factoring algorithm that I've discussed and quantum chemistry simulations. And then there are those problems like the backtracking and the search and satisfiability problems that allow for a polynomial speed up that, for example, use this quantum walk formalism. And then there is a big group of problems that have no speed up, and we will hear in one of the talks after me a little bit about this, where you have to think about problems that are really, really hard. So quantum computer cannot have any advantage over a classical computer, and also problems that are really, really easy, like sorting and binary search. But you will see later in a talk of Subhashri Patro that the edit distance is also one of those problems. But for many, the good news is that for many problems, we don't know yet in which category they fall. And this is precisely a big focus of our research, to develop on one hand quantum algorithms and to develop on the other hand tools to show the limits of this quantum algorithm, so the upper and the lower bounds. Another area in which this pertains is that of quantum cryptography. And this is maybe the most urgent one, because you might say that it's not a problem to have a quantum, to worry about your cryptographic security, because quantum computers will not be around for maybe the next 10 to 15 years, at least not the ones big enough to threaten current cryptographic schemes. And that may be true, or it may be sooner, I don't know, it may be later, but nevertheless, all the information that we send now over the internet and that uses this cryptographic security that can be broken by a quantum computer, that information, although it's encrypted and cannot be read now, it can be stored and it can be read, it can be decrypted once this quantum computer is there. So if you want your information to be secure well into the future, you already have to act now. That's why this is an important area for future secure cryptography. You really have to use quantum proof. I call it encryption now. And here we have two flavors. And the first one I already alluded to in one of the earlier slides, where I said you can use quantum mechanical properties, quantum physical properties itself to construct cryptographic schemes that are secure. And the first example is that of key distribution, but there are other ones like quantum position verification that we work at CWI. And then there is the way that doesn't use any quantum mechanics at all, that just uses classical cryptographic schemes that are secure against the quantum computer. And this is called post-quantum crypto. And there are examples using lattice-based cryptography, decoding of error-correcting code, hash-based, and many more. And this really is the realm of the crypto group at CWI. This will also be part of the Spearpunt security that will have a session later in the year. Of course, so you will hear more there. And of course, there is the combination of these two approaches. So this quantum software is extremely important, and a few years up till now, and it's changing rapidly, most of the focus was on building quantum hardware, building qubits, and much less effort was put onto what can we do with this quantum computer. But I think that having a good idea of how you can use this quantum computer is equally important as building one. And so that's why in 2015, we launched the research center Quantum QSoft, which is a joint enterprise between CWI and the University of Amsterdam. And we had our 5th year anniversary in December. And here you see some overview of the talks and the festivities that we had then. You can still see some of that back on the QSoft website. And in addition to developing QSoft, in 2017, we got a reasonably big grant from the Dutch government, one of these gravitation grants, to form the Quantum Software Consortium between Amsterdam, Leiden, and Delft. And I will say a little bit more about that too in the coming slides. But that was a nice addition to QSoft, and that helped us form sort of a community within the Netherlands that is working on quantum information at large. And so QSoft has a couple of themes. It has, as you see, 4 themes. Currently, we have about 25 permanent people who are not full-time, but some of them are full-time working on QSoft-related areas. I have a bunch of 20 PhD students and postdocs, and it borders on computer science, physics, and mathematics. And you see here that we have these 4 research lines, where research line 1 and 4 are really focusing on building new quantum algorithms. The first one is building them on noisy qubits, the ones that are coming out of the labs as we speak. And the line below, line 4, is really thinking about more stable quantum computers that hopefully will come out of the labs in the near future. Then here on the right-hand side, you see this theme, cryptography in the quantum world, which sort of is also partially done at the, at least the post-quantum crypto part is done at the crypto group at CWI. And here on the left-hand side, you see the more basic foundations of quantum information, which we call quantum information science. And so within CWI, there is a connection with a bunch of groups, of course, with the algorithms and complexity group, of which I am a member, but also with the network and optimization group, and also with cryptology and security. For obvious reasons, there are connections. And also more recently, we talked to computational imaging group, and there may be possibly others. And I want to repeat here Ronald's invitation that everyone who wants to learn more or who wants to help or has some ideas on this is very welcome to get in touch with us. Another thing that came out of this, and predominantly it came out of the Quantum Software Consortium, that is this joint enterprise between Delft, Leiden, and Amsterdam, and that's that legal and societal issues are becoming an important role, and that needs to be addressed. And in this consortium, we also have something that we call the Legal and Societal Board. And there's nice meetings, as you can see here. And there even is one PhD student and a postdoc working on scientific problems that are related to this. And this legal and societal board, it organizes meetups and meetings to discuss these issues. Actually, I find it extremely interesting, and it somehow came a bit as a surprise that this was something that was so interesting to look at. Okay, so another thing that came out of all of this is that we got a nice interaction with industry. We have projects running with Bosch, and you will hear about that, ABN AMRO, and recently we also hooked up with Toyota. And because of these, and the predominant question here is, how can quantum computer help my business? That's the question we get. And then if it can, then how can we make use of it? Can we get what we call quantum ready? And because of this, and because of the previous slide on the legal and ethical sides, we have added a fifth research line to QSoft, which we call Quantum for Society and Business. And moreover, the national program has taken off as well. And so we have set up something that we call Quantum Amsterdam to have this to make sure that we can transfer the academic knowledge into the society and industry. And Quantum Amsterdam, which was founded in 2020, last year, it is a quantum hardware and software applications hub. It facilitates and helps building an ecosystem here in Amsterdam and also in the Netherlands, where it ties into, it will enable, as I said, this interaction between industry and academia. And it has workshops and outreach and meetups and a startup generator. And it connects and coordinates with the Dutch larger national landscape. Here you see a schematic of what we're doing. Christian Schaffner is in charge here. So if you want to know more about this, you should get in touch with him. And you see here, this was, again, a sort of a joint venture between CWI, University of Amsterdam, and QSoft is also involved with this. And so this Quantum Amsterdam somehow connects up with the larger national quantum program, which is called the Quantum Delta Netherlands. And the national quantum agenda, or Quantum Delta, was a research proposal nationwide that we wrote with the partners that you see here below. So the Quantum Software Consortium partners, QTech, Leiden, QSoft, and Economic Affairs and Climate, TNO, NWO, Eindhoven, Twente, Leiden. Well, the Leiden is already there, and there are other entities that you may not know, TechLeap and AMS-IX, but also Microsoft is involved. And the idea here is a national-wide program that focuses on realizing breakthroughs and innovation. You see it all here on the slide. And it has these three programs. Let me go to the next slide. I should say that this was written and then given to Mona Keizer, who you see here on the picture, and then Robert Dijkgraaf gave this, sort of presented this program to Mona Keizer at the Secretary of State of Economic Affairs and Climate. And here you see a little bit better scheme of what this program contains. It has three catalysator programs, one focusing on quantum computing, one focusing on quantum internet, and one on quantum sensing. And there are four action lines, where the first one is actually interesting for everyone here at CWI as well, because that is about basic research and innovation. Then there is one that focuses on ecosystems and market creation and spin outs and so on. Then there is a whole line dedicated to human capital, education, and knowledge skills. Here, education is sort of the key word, and the last one is one that deals with this legal and ethical aspects, starting a dialogue about quantum technology. And here you see that in a nice scheme. And then in 2020, we were already awarded a starting grant of 23.5 million in awaiting of a larger sum of money that we applied for. And this already allowed us to start up a couple of these of this subset of the program written here. So it allowed us to start CAT 1 and CAT 2 and some of an action line 2. And we received in Amsterdam already a bunch of PhD students. 4 went to the University of Amsterdam and 2 went to CWI, and we got funding to start up Quantum Amsterdam, the hub that I told you about, and a new hub that we are starting, a field lab. It's called Quantum Applications Lab, to host these PhD students and to have them interact with industry and society. And then the big news was a couple of weeks ago that the application that we applied for at the Groeifonds, the growth fund by Hoekstra and Wiebes, that was funded fully, quite amazing, and 650 million euros now fund the whole program that is written here. And so more of this is coming to Amsterdam.
Sorry, Harry, to interrupt you. Could you say what sort of fraction of this 600 million will actually go to CWI? Is there any estimate of this?
Oh, yeah, so that's sort of the wrong question to ask. Sort of the spirit of the program is that we are building a program together. And there's lots of programs and ways to obtain money. For example, yeah, I can't go back for some reason. I want to go back. Let's see if I can go back. There we are. So, for example, in this action line 1 here, where realization of research and innovation, 42 million has been set aside to pure research. So that's this blue bubble here in the middle, and this will be made available through calls of NMO. And so yeah, it's hard to say. I mean, but if we write reasonable proposals, then a part of this money can come to CWI in Amsterdam. But it's really a national program, so it's probably not the right way to look at it as how much can come to Amsterdam.
Okay, I see. Thanks.
But you can imagine that a reasonable fraction of this, if we do things right, will end up here. So, ending my presentation, I see this larger feedback loops or picture emerging, where on the left-hand side here you see what I call the hardware cycle, and that was also the cycle that was initiated by the Quantum Software Consortium, where on one end you have computer scientists and mathematicians that come up with beautiful algorithms, and then on the other hand, on the bottom, you have the experimental physicists and the engineers that actually have real hardware. And then when you try to implement your beautiful ideas onto the hardware, it turns out that the hardware doesn't work, it's noisy, or it doesn't have the ability to do what you wanted to do. And so you're going back to the drawing board and you engage in this cycle, which we call the hardware cycle, where your protocols and algorithms are refined, and also the hardware hopefully is refined and adjusted due to the wishes of the programmers and the quantum algorithm designers. And this cycle is in full swing now. And we were very happy that Jonas Helfsen, who will talk about this part, he's waving now, he has recently accepted the tenure track position on the Quantum Software Consortium at CWI, doing these kind of things, and he will talk about a little bit of the things that he is doing and is planning to do. Then on the other right-hand side, you see here what I call the industry cycle, where there is a similar thing going on, where on one end you have mathematicians and computer scientists who know about quantum computing and quantum algorithms, and on the other hand you have industry and industrial use cases, and industry doesn't really know much about quantum, but they do want to know if it's useful or not. And on the other hand, we know a lot about quantum, but we don't know what's useful for industry. And so a dialogue, also a cycle, has to engage here, where Again, you have the mathematicians and computer scientists on one hand who will talk to the people in industry, and this dialogue also is going on, and it makes clear what kind of algorithms are needed and what kind of problems we should focus on. And here there will be the second talk in the afternoon will be given by Subhashri Patro, who will talk about some of the results that she obtained in her project with Bosch. And so these, and so you see that these two spinning, I'm almost there. So these will spin at different speeds, and they sort of have to be geared by some gear block to sort of be combined together. And I think this whole picture is what should be implemented. And you see that in the middle there's QSoft Quantum Delta and Quantum Amsterdam, and of course also the quantum spearpunt at CWI figures prominently in the middle here. So indeed, Ronald already said, so this quantum spearpunt at CWI is of course the QSoft projection at CWI. That's sort of the kernel of that, but then the spearpunt at CWI might be a little bit bigger, and it will be the combined groups who want to get involved, and machine learning, SWOT, and computational imaging are groups that are potentially already showed some interest. And in this respect, I am happy to announce a couple of new projects that we are starting, and there will be some joint workshops there. So there's a quantum chemistry project that is running with the VU, and which has one PhD student and one postdoc. Then the people from the Einstein telescope who work on gravitational wave detectors, that's located hopefully in the Netherlands and Limburg in the next 30 or 40 years. This is a really big project, and they are looking for ways to use perhaps quantum computers to help analyzing their data. Similar thing is true for the Large Hadron Collider for data analysis, and this is all just explorative. We don't know if this is going to be useful, if quantum computers are useful here or not, but at least we are talking to these people. And then more recently, there's a weather and climate project funded by Surf-Sara with the University of Wageningen. And here the ray tracing technique and the computational imaging group at CWI has shown interest to join this discussion. And even more recently, there is a radio astronomy project starting with the eScience Center and Surf-Sara. There's a mistake there on my slide. And here the goal is to detect quasars in the sky. And the question is whether quantum algorithms could help with that or not. So with that, I want to end my talk. So anyone interested, please contact Ronald or me or anyone else who, for example, Jonas or Suba. But for this, I'll end here, and I would like to leave the floor to Jonas and Suba for the next talks.
Okay, thanks, Harry. Let's give him a bit of applause. We have a few minutes for questions from the audience. You can either write something in the chat, or you can use the raise hand function in Zoom. I see Yannis, maybe you just unmute yourself to ask your question.
Yeah, let me put on my headphones. Yeah, so I have one question. Maybe it's too early for this question, but I was curious. So from the point of view of developing quantum software, is there any preference for particular hardware implementation of a quantum computer? For example, in terms of the instruction set that this quantum computer could provide, or not? Maybe, yeah, I don't know.
Yeah, so good question. Indeed, from a software point of view, this is important because there are actually a bunch of platforms out there that try to build qubits in different ways. As soon as you have a system that has, say, two different states that you can access and that you can bring in superposition, then in principle, you have a possible way of implementing qubits. And so there are many ways doing it on photons, or doing it on trapped ions, or doing it in so-called solid state qubits, and there are a few more. And all these systems have their peculiarities, and addressing these systems is done in different ways. And indeed, if you want to use these systems to the fullest, if you want to get all the juice out of them that's potentially in there, you have to address them in a different way. So you will have different ways of addressing your software. But on the other hand, very much like classical computing, you are also developing algorithms in a hardware agnostic way. So for that, you really don't need to worry much about the hardware. But once you want to implement it and really get something running, you have to change your algorithm and massage it so that it can work with the particular hardware. And then maybe one particular platform is more useful than another. That could very well be.
Okay, and then there's a question in the chat by Fons Kuik, namely, what is quantum sensing? I guess this was one of the topics of the national agenda. Maybe you can say briefly, what is quantum sensing, Harry?
Yeah, so quantum sensing is one of the more earlier physical applications of quantum, sort of quantum information 2.0, because quantum mechanics already has had many applications in our society and our industry, for example, lasers or solar cells. But more refined way, sort of the quantum physics 2.0 can be seen in quantum sensing. And here you can think of, for example, at the UVA, Florian Schreck is heading a big project on quantum clocks, where you use quantum physics and quantum interference and superposition to build extremely precise clocks, which then in turn can be used for wireless phones, or for detecting, funnily enough, detecting materials in the ground without opening up the ground. So sensing is along those lines, using quantum mechanical effects to, for example, build very precise clocks.